How's it going?
Good.
Good? It's good. Let's see. Yeah, today is recursion, which is going to be the second hardest section to teach. So I'm excited. Next week. Yeah, next week is recursion backtracking. It's like recursion, but tougher. So that one is really hard. This one is like, okay. Okay, so you mean like pointers, binary search trees, that kind of stuff? Okay. Okay. All right, cool. Okay, cool. All right, sounds good. Week 8, yeah. Yeah, so you got a lot of time. All right, and our section is pretty small, although I hoped at least out of the small section everyone would show up. So let's see, Sandra, Eric over here, okay, and then Joel. Yeah, I know. What? Jessica. She went to another section at the same time, actually. Yeah. Hey, I'm attributing that to the fact that we're being recorded, and not everyone wants to be recorded. Sure. Yeah. It's totally not because of me. I don't have a red marker. Okay. Whatever. All right, we're gonna start it in like 1 minute. Okay. One second. Let me see if more people show up. This is kind of sad. Okay. I'll just double check. All right, well, I think we have to get started. Yeah, so thanks for coming back. So our section only currently has 3 students, and hopefully more students will show up as the section goes along, okay? But but otherwise, thanks for coming, and let's get started. For some announcements, for SCPD students, I was recently talking with Kate, and especially because I don't have a lot of students, so if you have any questions about section in particular, my email address is written up here, so feel free to email me if you have questions. I think this email is also listed on the SCPD handout that Kate sent you, so feel free to email me if you have any questions about section. All right. If you have questions about how your assignment was graded or about like some of the feedback that you got, email your grader, and your grader is listed on your CS198. If you log in to where you sign up for section, you can see who your grader is. Okay? Yes, because I don't grade your assignments. Now, let's see. So specifically for my section, even though we don't have a lot of people right now, IGs. We'll probably do IGs either today or tomorrow, depending on when you're free. Maybe Saturday. Hey, come on in. No problem. Yeah. So we're just talking about IGs. When would you be free, like today and tomorrow, or Saturday? What time works best for y'all?
I'd rather not. Saturday. I could come in today between here and 1:30.
Yeah, 1:30. Okay. Anytime after 1:30.
Maybe after 3:30.
3:30. Okay. All right. Yeah. All right. Sure.
It's individual, right?
Yeah, individual. Yeah.
Okay.
Yeah. And then, are you two partnering up for the next assignment? Okay.
Cool. Well, not for this one.
Okay.
Well, we're working together, but we're just gonna do it separately.
Sure. Yeah. That's fine. Yeah. I mean, I only have. So just for you to, so you know, I only have 3 students in this section.
Okay.
So yeah, I will put a lot of comments on your submissions for sure. Yeah. About office hours. So I promised office hours, but we only have 3 students, so you can literally decide if you want help if you want help, just tell me like at least a day in advance, and then we can meet up sometime to meet. Okay? Yeah. All right. How's assignment 2 going?
Pretty good. We kind of went through the algorithm and did like the pseudocode and stuff.
Okay.
Yesterday, and then I think we got it pretty well planned out.
Okay. Trying to get it in by tomorrow, or
yeah, that's the idea.
Okay, cool. All right, yeah. Yeah, Ngrams is I think it's a pretty cool assignment. It's
pretty sweet.
Yeah, it's pretty cool. Like I know you can put in like song lyrics from like your favorite artist, and you'll get like something cool. So yeah,
right?
try
If you
that.
read in all the big pop songs,
Yeah.
then you could create a new pop song and be famous, right? It's like the same formula. You just put a little words together, same kind of beat, and you can make a lot of money.
Yeah, that's true. Like I think there's an input file called like Lady Gaga or something.
Oh yeah.
I think that's like one of the input files. So you just put it in and you get a new pop song.
Awesome.
Yeah. Okay. So today we're gonna talk about recursion. Recursion is definitely one of the more challenging topics of the class. And what I feel is super important about recursion is that everything else in the class, after we're gonna spend 2 weeks on recursion. This week is like the simple recursion. Next week is like recursive problem solving. Yeah.
There you go.
Next week we'll be covering like recursive problem solving, backtracking, and like that forms the core part of the class.
Okay.
Yeah. And then after that, then you'll get to like more. Then we'll get to more from high level algorithmic like recursion, backtracking to more concrete level items like how do you manage memory? How do you deal with like more computer system type stuff? Okay. So, but then even after we get to that point, a lot of what we do will be recursive. So I'd say these 2 weeks are like the most important weeks of the quarter. Okay.
Okay.
Yeah. Do not worry if you don't understand recursion initially.
Okay.
I know there's been like 2 recursion lectures, and then today we're gonna talk about recursion again. Just the key part for recursion is do as many practice problems as you can, because soon you'll realize that all recursion problems are kind of similar.
Yeah.
And that includes the recursion problem you'll get on the exam. It's kind of similar to a bunch of practice problems that we'll do. So yeah, the key part is just do a bunch and you'll get used to it.
Cool.
All right. Cool. Cool. So today we're going to talk about So we'll do a quick review of recursion. Then we're going to do a couple examples. 3 of these are code problems, and 1 of them is a trace problem. Okay. So on the exam, you'll get 2 kinds of problems. A trace problem is where you're given a chunk of code and you just have to see what it prints. Kind of like what we did last week. Okay. For recursion, those are a little tricky because you have to keep track of like how many recursive calls you're in. Okay, so we'll do an example of that. I've developed like a sort of like a strategy that you can use just so you don't confuse yourself. Okay. Because I remember confusing myself during the exam. Yeah, and then we'll go through like 3 fairly simple recursion problems, and we probably won't have time because I always am super optimistic about time. But there is a pretty challenging problem at the end, which uses recursion in a pretty advanced manner. Okay, it's like you can't really solve it it's hard to solve iteratively if you don't use recursion for the last problem. Okay, cool. All right, let's quickly do a review of recursion. So let's do a quick review. So recursion, what is the key idea behind recursion? Why is it called recursion?
You call your function whilst you're in the loop.
Right, yeah. So recursion, the basic idea behind recursion is your function essentially calls itself. So function which calls. All right. Let me pass a handout. Hi, Michael. Okay. Oh, okay. You're my section, right?
Yeah.
Oh, okay. All right.
10:30 BO3.
Yes. Okay.
Sorry I missed last week. I had a little bit of trouble finding the place.
Oh, sure. That's no problem.
Confusing for sure.
All right. Yeah. So recursion is essentially a function which calls itself. Okay.
Right.
And then why you'd want to do this? Well, we'll see a lot of problems that we'll do today. Usually, recursion problems are those which you can easily find at like a self-similar. You can find self-similarity within the problem. Okay. Yeah. When you're writing a recursive function, what are the two like important pieces of the recursive function you have to worry about?
Base case and like the iterative case.
Yeah. So one's called the base case, and one's called the recursive case.
So it's essentially going to be like an if-else kind of in the recursion. Okay.
Yeah, exactly. Although sometimes you won't just have one base case. You'll have like a lot of base cases.
Okay.
Yeah. Same for the recursive case. So, but definitely when you write recursive code, structure the code so that you clearly see base case, recursive case.
And so you can have many base cases, but only one recursive case, because otherwise. Usually.
Yeah, sometimes you might have like multiple recursive cases depending on what you want to do. And then our first example will show you like when you might want different recursive cases.
Okay.
Yeah. Yeah. When you write your code, be sure do not just mix these up because recursive code is already really hard to understand. If you mix these two up, it becomes like impossible to figure out what the code is doing. The most important part is by looking at the base case, you should easily be able to see when the recursion stops. Okay, that's the whole point of the base case.
Okay.
Okay. Cool. I think I said the answer already, but like, what does the base case do? What's the important part you have to put inside a base case?
What's the end of the recursion from which you start going up again?
Yeah, exactly. So in the base case, it's when the function does not call itself anymore. Okay. Usually, the base case. If you reach the base case, that means your problem is simple enough that you don't have to do any more work to solve it. You can immediately say what the answer is. Okay. You remember Marty's? He gave two examples on Monday. One of the examples was the count how many people are sitting in a row. Right. For that, what was the base case?
The last person at the top.
Yeah, because if you were sitting at the very back and Marty asked you how many people are sitting behind you, well, you can say, oh, there's no one behind me, so including myself, there's only one person. Right? Yeah, it's when the answer is just so simple that you can immediately solve it without doing any more work. Okay, today we'll see like different ways that you might do recursion. As a really simple guide, oftentimes for a string problem, if you had to pass strings around, what would be like the simplest possible string?
An empty string?
Yeah, empty string, exactly. Right? Because oftentimes when you get an empty string for a function, there's like a really obvious answer to that. So for the base case for string problems, you'd usually do like what happens when you get the empty string. Okay. How about like collections, ADTs? So vectors, stacks, queues.
Empty queue.
Yeah, exactly. Same idea. So oftentimes you'll sometimes like be removing elements, but usually at the end you'll see, oh, I have no more elements left. I know the answer immediately. Okay? Yeah. So the base case is when the problem is simple enough to solve. Okay? Now, what happens in the recursive case? How is the recursive case different from the base case?
You call the function again with a different parameter than what you call the function with.
Right, yeah. So inside of your recursive case, you will call the function again. Okay, and then you mentioned a really important point, which is with a different parameter, right? So you can't just pass any parameter. You can't just pass in the same parameters.
It'll go in a
Yeah,
infinite loop.
Yeah, if you do that, then like your program will infinitely loop because it will just continually call the recursive case. Okay. The main idea is the parameters, how you change the parameters. They have to have like forward progress towards the base case. Okay. So for example, in a string problem, if your base case is the empty string, what does forward progress mean in this case? So if I gave you a string, 106B, how do you make forward progress towards the base case?
Items.
Yeah, exactly. So to go towards the empty string, you'd probably have to move characters around. Okay? Yes?
So is one of the goals of a recursive function to try to get towards the base case then? So you're trying to edit whatever your parameters are to like make it so you actually reach the base case eventually.
Yes. Yeah. So yeah, you're exactly right. So and then that's like that's what happens if you try to trace through all the function calls. Then your goal is, oh, at the end of all the function calls, you should reach the base case.
Okay.
Okay. Now there are two ways to think about recursive functions. Let me pull this down. Okay, and this is like a really important like two different ways to think about recursion, and I think this is really important because some students think there are two ways to think about recursion. If you use the wrong method to think about recursion in like the wrong place, then you'll find a hard time writing the recursive code. Okay, there's two ways to think about recursive functions. Recursive functions. You can think of it in either one is called you just trace everything. So trace all the stack frames. Trace all stack frames. Okay, and we're gonna do one of those examples where essentially you plug in the parameters and then you're gonna try to look at all the parameters. Every time the function is called, you're gonna look at how the parameters are changing. You're gonna look at every single function call until the base case. Okay, that's really useful for trace problems because you literally have to do that for a trace problem, right? If I asked you, what does this code print? Well, you actually have to go and trace through all the recursive calls. But the other way to think about the problem is abstractly. Okay? This is super important when you write code. All right? When you are writing, when you're trying to develop a recursive function for a problem, don't think too deep about like, okay, after I make a recursive call, what happens after all those recursive calls? Okay, because that will like confuse yourself. You're gonna say, oh, I make like, remember what Marty said? You make one step of progress, the minimal amount of progress. Beyond that point, don't think about what happens after you make the recursive call. Okay? I think Marty will use this term next week. It's called the recursive leap of faith. What you do is, since your function calls itself, assume that your function works. Okay? So assume your function, the function that you'll call recursively, assume that function already works.
Okay.
Okay? So this might seem a little abstract right now, abstractly, but we will do like an explicit example right now. Okay? Cool. So the first problem we're going to do is pretty straight, simple. Let me remove my answer. Okay, there we go. So the first problem we're going to write is called digit sum. Okay, and what this problem should do is essentially you're going to pass in a parameter, which is an int. Okay, so it's going to be some number. And what you want to return is you want to return the sum of all the digits. Okay? So we want to return another int, which is the sum of digits. So just as a couple examples, if I had 1, 2, 3, 4, so this is input, output. If I had 1, 2, 3, 4, what would you return?
You return 10.
10, right? Because 4 plus 3 plus 2 plus 1 is 10. Okay? Some other like odd ones. If you had like 600, what would you return? 6. Okay. Yeah. There might be something going on with the zeros you want to be careful about. But yeah. Otherwise, if the zeros, just add them up in the same way. All right. Okay. And then this is a little bit trickier. What if you had negative 2, 3, 4, 5? So.
Be like negative 14.
Yeah. So as stated on the example on the handout, if you have a negative number, essentially just add up all the digits as if it was a positive number, but just make it negative. Okay. So 4 plus 3 plus 2 plus 1, that's I can't do math. 7, 14, negative 14. Okay. Any questions? Okay. this is also super important on like exams because there's usually 1 point for this. You sometimes have to think, okay, are there any invalid inputs? Okay, and you can look up here, are there any invalid inputs you have to worry about?
And do we know it's always going to be a integer? Like, so what if somebody tries to type in a double? Will that throw an exception automatically, or do we need to code for that?
Yeah, so for that, essentially, the code won't compile if whoever is calling this function passes in double. Yeah, so those errors are like the compiler will catch those, so you don't have to worry about those. Yeah, for most problems, you can just worry about the like edge cases or invalid input that they mentioned in the handout. Okay, you can assume that whoever's calling your function will follow the handout exactly. Okay. So yeah, there are no like other weird cases we have to worry about. Maybe 0, right? What would 0 be?
0.
Yeah, okay. So don't have to think too much about that. Although this might give us a hint to how we write our recursive function. Okay? Awesome. All right, let's... Oh, great. These whiteboards are awesome. Okay, so we're going to write, let's write some pseudocode first, and then we can quickly code it up, okay? Pseudocode. So we're going to write a function called digit sum, and then we're going to try to write that recursively. Now, think about 1, 2, 3, 4, right? Given this integer, how can we make one step of progress towards finding the sum? How do we make one step of progress?
Divide by, call it and divide it by 10. Like 1, 2, 3, 4 divided by 10. Put that in the function.
Sure. So what I'm hearing is, yes, so that's exactly what you would do. And then the whole idea that you're trying to go after is, focus on one digit at a time, right? So this is like a good way to think about recursion. Think about the first thing, or one digit at a time, one character, one item, one digit at a time, and pretend you can't see anything else. Okay. So for right now, you mentioned divide by 10. So I'm guessing you're focusing on this digit. Okay. I'm gonna focus on this digit right now, 4. Okay. So I'm gonna write the 4 somewhere. Now, after you have this 4, so suppose we now just ignore this 4. How is the problem self-similar with regard to the other 3 digits? How are these 3 digits relevant to solving our problem?
It does the same thing, right? Like you want to isolate 3 and deal with 3, and then isolate 2.
Yeah, you're exactly right. One thing I'd caution is when you write a recursive function, don't think about what you're going to do to like 3, then 2, then 1. Okay, think very abstractly. What does our function do? Our function is called digit sum, right? Digit sum, what it should do is it should calculate the sum of the digits of something. Okay, and this is the key part about assuming your function works. I think I wrote that up there. Assume your function works. Abstractly, after we've isolated the 4, what do we want to do with this generic thing that follows?
Have a new function that, like, we call the function with this new number.
Sorry, can you repeat what you said?
Yeah, call the function again with the new number that we have.
Yeah, because abstractly, we have a 4, and then we also want to find the sum of the digits of this remaining number, right? So how does our big problem break down into a little smaller problem? How did our big problem, 1, 2, 3, 4, break down into a slightly smaller problem?
Well, I guess your base case would be you can't divide by 10 anymore. Then you've gone through everything. And if not, then you keep on dividing by 10 to like make it smaller and get each digit.
Oh, great. Okay. Yes, you're exactly right. We're already jumping a little ahead. Yeah, don't worry. Yeah, so that is definitely what the base case is, okay? So is it clear what I mean right now? So let me write this diagram in another way. Let's see. Let me write this one more time. To solve 1, 2, 3, 4, I'm going to have a box, and I'm going to call digit sum on 1, 2, 3, 4. That is equivalent to, okay, we can first isolate the 4.
So 4 plus digit sum of 1, 2, 3.
Right. Because to find the digit sum of an entire number, you can think of it as, okay, we're going to isolate one of the digits, and then we're going to find the digit sum of the other 3. Now, you might wonder, all right, how do you find the digit sum of 1, 2, 3? Isn't that exactly the function we're writing about? This is where you think about that recursive leap of faith. Assume that this function works, okay? Assuming that this function works, you can just call it, and then this will give you the correct answer. So abstractly, think about what does digit sum of 1, 2, 3 give you?
The sum.
Which is 6, right?
Yeah.
So this thing will give you 6. And then after you make the recursive call, how do you combine this thing that you isolated?
You 4 plus the digit sum of 1, 2, 3.
Right, exactly. So because we isolated this out, we found the digit sum of this. To find the digit sum of the whole thing, including the 4, you just add the 4 through. So 4 plus 6, you get 10.
Okay, so like you said, you're not really thinking about, all right, breaking down, like drawing off like the 3 and then the 12. You're just thinking about after doing the first recursion, just like believing that.
You're exactly right. All right. Do not worry about what happens after this, okay? Because remember, inside when we write the code, you're only gonna write the code for one step, and you can assume all the other steps work.
Yeah.
Don't think too much about what happens later, because if you do, then you'll try to like, oh, okay, what happens after the 4? Then I do the 3, then I do the 2, then I do the 1. Yeah.
10 digits.
Yeah. Worry about one digit at a time. Okay. Another way I like to put this, like a puzzle. Sometimes I like to do this. I don't want to write this here, but I like to think of a puzzle like this. So suppose you had a number, but I don't tell you what the digits are. Okay. But I do tell you the last digit is a 2. Okay. Assuming that your function works, how can you find the digit sum of this thing?
Does the computer know the other digits?
Yes. So if you pass this thing into the computer knows what the digits are, but you don't.
The same thing you just did.
Right, exactly, right? Digit sum. So you find the digit sum of this whole thing is equal to, you do the 2 plus the digit sum of whatever the heck that is.
Okay.
Okay?
So you just go, just figure out.
Yeah.
To get the 2.
Yeah, exactly. Don't think too much about what is over here.
Yeah.
Only think one step, this 4. This 4 is the only one that matters. Okay? Does that make sense? Okay? And then in this example, in our recursive calls, each one is going to return a number, right? Like this one is going to return 6. And then we can use that result we can combine that result with the 4 to get our 10. Okay? So for our pseudocode, which case does this fall under? Is this the base case or the recursive case?
This is recursive.
Recursive case, right? Because we make the recursive call. Recursive case. Okay. And then what would the recursive case be? So ignoring whatever happened in the base case, what would the recursive case be?
Return like the value you have, so like return digit sum of x divided by 10, something like that, plus x modulus 10.
Sure, yes. We're going to write the code specifically later, but I'm just going to, on a high level, say return the last digit plus the digit sum of all other digits. Okay, yeah, you're exactly right. We use mod and divide to get those items. Okay, cool. All right. So that is our recursive case. Essentially, the idea is, okay, we make the recursive call on all the other digits. We isolate this one digit, and then later on when we do the digit sum, we can add this digit sum with the last digit. Okay. Now, I find it easier to write the recursive case first because then you have an idea of where the base case funnels to, right? If you kept repeating this procedure, what happens?
Stack overflow. I mean, without a base case.
Yes, without a base case, then you have an infinite recursion, stack overflow. So you definitely need a base case over here. And to figure out what the base case is, think about what happens when this continues. So now you actually want to think, okay, if I kept repeating this, when can I no longer do this anymore?
When you only have one digit, and so it like the all other sum is basically that's your
Okay, so let's see. So you're saying if we only have one digit left?
or maybe 0 even. 0
Okay.
digits.
So when we have one digit left, yeah, we could put that as a base case. So we could say, oh, when there's only, when your sum is less than 10, then just return that digit, right? Yeah, but you also mentioned something else after that. You mentioned 1 or
0.
0. We could have 0 digits. How would that work? So suppose you had like just the one digit sum of 1. How can you, if we just said, okay, this is not our base case, let's just go even one step further. Well, what would we get?
Or we get 1 on the right side, and the other is digit sum of 0.
That's 0. I mean, no, digit sum of 0 is 0. Right. So now you can see there's 2 ways to put the base case, right? We can either put the base case here, when there's 1 digit left, or when there's 0 digits left. Which one's better?
Honestly, I would say 1, just
1?
because you can just return whatever that digit is.
Yeah. You make a fair point, which is like, okay, I mean, here, if it's just 1, then why don't you just return it, right?
Because 0 will have no effect on the function, whatever. It would just be an extra call.
Yeah. So yeah, I totally agree with you that that there's no, like, you cannot really see like a clear point in doing this call. Yeah. Although in general for recursion, try to make your base case as simple as possible. So like all the recursive cases, try to like funnel it towards 1. I agree in this example, there's like not a real point in doing that, but later on we'll see more examples where, if you stop a little bit early, there's like more cases you have to handle, okay? Yeah. Here, you could certainly do like, if it's less than 10, then just return the digit. But notice that it's really nice how everything, if you just kept going one step further, everything funnels to 0, which is kind of nice, okay? All right, yeah. So in your, when you do your assignments and your, on the exams, we don't really care which one you choose, but on your assignments, try to go for the simplest one possible, okay? Cool. So let's see, what would the pseudocode for this one be?
I guess a digit sum of, I guess, last digit equals 0.
So if digit sum of last digit?
Or
just the parameter, right? The number.
yeah, sorry. The
What are you calling the parameter, by the way? Just digits, perhaps?
I thought you were calling it,
Okay.
last digit.
If we'll call the parameter something when we do the code. If the parameter is 0, then
And then just return, I guess, what would be, I guess.
0. Yeah. Okay. All right. Are you done?
If the base case is valid and the recursive case is valid, then we are basically done.
Yeah. So we're pretty close to being done. All right. There's just one more thing you have to worry about. When you're done with all this, double check all your cases.
Oh yeah, the negative.
Is there? Yeah. Don't forget we have to deal with this negative, right? So we're almost done. On an exam, if you do this, you'll get 8 out of 10. Probably 7 out of 10. Okay. So how do we deal with the fact that, okay, what if you have a negative sign here? Actually, I don't want to use this diagram. Let's write another diagram. I don't want to cover my function. Okay, whatever. If we had a negative sign here, so this is the third one, negative 2, 3, 4, 4, 5. How can we handle this one?
You could either do it like just at the interval.
I guess at the very beginning, which, right? And if it's negative, then you just subtract everything.
Okay, so you're saying if it's negative initially,
Yeah.
then just say, okay, it's negative. And then what would your recursion, how can you continue? So, okay, it's negative, sure.
And if the
Yes.
parameter is negative, you multiply it by -1, and then you multiply it by -1 again before you return it.
Yeah, that's a very good, very good strategy. So you essentially make the recursive call on 2, 3, 4, 5, and then whatever digit sum you get here, just multiply that by -1. Okay? Yeah. So what would the pseudocode look like?
Well, it's before the loop.
It's definitely before this one, right?
Mm.
Okay, so how would you deal with that? This is technically also a recursive case, right? Okay, recursive case. How do you deal with the negative case?
Well, would you want to have it in your recursive case because you only want to evaluate it actually like once because the whole number is going to be negative. So I would even suggest maybe putting it before your base and recursive case and just having a negative flag or something. And then at the end,
So you mean like a negative flag which you pass around as a parameter? Yeah, yeah, I think we could do that. Although, because that requires like an extra parameter, right? And then, because right now, Michael, right?
Yes, and I think that you could go even simpler than that. If you put it at the beginning, if you say, like, say if parameter is less than 0, which is going to cover all negatives, then we could just do the recursive thing again, where we just call this, like, make the parameter positive by multiplying by -1, and then call this function, and then return the result of some digits but multiplied by -1.
Yeah. Yes. Yes. That was exactly what you're suggesting over here, right? Yeah. So the idea is,
two separate ones.
yeah. So if it is negative, you can still use this function that you have. If I just multiply by -1 and find whatever digit sum this is, and then when you're done with that, then you multiply that by -1. Because 2, 3, 4, 5 is going to give you 14, right? And then you can just multiply that by -1 to get -14. Okay. And yeah, you mentioned a really good point, which is, should you put it before or after the base case, right? In this example, you can put it in both because the less than 0 and the equal 0, they don't conflict, right? Whichever one you check first, the order in which you put the cases don't really matter in this example because 0 and less than 0 are different. But because you technically are going to make a recursive call, I'm just going to group it within the recursive case, okay? So if parameter less than 0, then return digit sum. Negative parameter times -1. Okay? Does that make sense? Okay? And then let's see. We can quickly code this because, I mean, this is literally the code. Okay, let's see. So digit sum. By the way, one thing, oftentimes these problems don't give you the headers. Just make it a good practice when you do the problems. Try to come up with the headers yourselves because on the exam, you always get 1 point for writing the header. Okay, so don't get the header wrong. Okay.
And we're not creating the header, we're just copying down the header that's given to us.
So Marty doesn't give you the headers. Okay, so Marty doesn't give you headers, so you have to make sure you write the correct header. Okay, including the return type, each parameter, and also what's really tricky is sometimes you'll say, the parameter is a reference to a vector. Okay, that ampersand will cost you a point. So this is just like an exam thing. Make sure you copy that. Okay.
But I guess like on the exam, are we going to be given the name of the function, or do we get to name the function ourselves?
Yeah. So you'll be given up here. You'll be given. This is kind of like an exam problem. You'll be given the name of the function, and you'll be told what the parameters and the return types are.
Okay.
Okay. You can call the parameter whatever you want, but just make sure you just follow the parameter and return type. Okay. All right. So let's see. How do you code this up? I'm just going to quickly go through this because this is literally the code. If it's equal to 0, then just return 0. Otherwise, if the parameter is negative, then you just return, what would you return here? Digit sum of?
Positive parameter. Like
Yeah.
So negative.
So -1 times the number, and then you make that whole thing negative, right? Okay. Otherwise, return digit sum. How do you get all the other digits? Except the last one.
Num divided by 10.
Exactly, yeah. And then you also want to add the last digit, which is
Num modulo
10. Okay. And just some good style issues. Make sure you have this. Okay. And then run it, and it's gonna work. Ooh, it even played it on speaker. Okay. So yes, that's one problem. Okay. How about this? Let's spend. I'm always slow on time. Okay. Let's spend 3 minutes. Talk amongst yourselves or try to figure out the problem yourself. And then we're going to do, this is a really similar problem to the one that Marty did in class about the, this is really similar to one of the examples he gave. Okay, so the idea is this. You have a stack which has like a couple numbers on it. And what you want to do is you want to make it so that you repeat a copy of each number. So before the stack looks like this, now it should look like 1, 1, 2, 2, 3, 3. Okay? I'll give you 2 or 3 minutes. Try to think about how would you turn a stack. You're given a stack with 1, 2, 3. Remember, the bottom of the stack is that 1. So if you pop, you get 3. How do you turn this into this? Okay? Does that make sense? And as a hint, this is really similar to an example Marty did in class. Yeah, my hint is it involves food.
M&Ms.
Yeah, M&Ms, yeah.
Okay, so we're going to want to remove everything and then put it back in twice. That's right.
Yes.
Yeah.
So have a second stack, I assume.
Yeah.
Like
Let's see. I don't think you can use another stack. Let's see. Yeah.
Do not.
Do not use any auxiliary collection.
yeah, we don't need that even. We can just do the recursive case.
Or we can pop it. Here's how we can do it. We can pop the top digit, then we can call it again. Like some sort of base case, if there's nothing left, then we're done.
Yeah.
Okay.
And then if there's something left in the stack, pop it. And then if you could some way, like in the recursive case, add what you just popped back on, like twice.
Yeah. That is a good strategy. Let's actually write it out. So suppose you had a stack which is like 1, 2, 3. So the first thing you said was pop off the first thing. Okay, so we're gonna pop off the 3. Or actually, let me write this. So this we can set that equal to. So you first pop off the 3. So you have 1 and 2. You pop off the 3, and then. So yeah, this is really similar to the previous example, right? We cared about the very first one. What do you do with everything else?
You recursively call it whatever stutter stack is this.
Yeah, because if you call stutter stack
You'll
on,
just keep on doing it until you get nothing, and then you return.
yeah,
And you add 'em.
what happens if you call stutter stack on this thing? What is the result if you call stutter stack on this?
I mean, it'll
Hopefully
return
1,
1,
1,
1,
2,
2, 2.
Okay, so if you call stutter stack on this thing, plus a 3. Okay, so stutter stack of this thing is equal to calling stutter stack on this plus a 3, and that gives you 1, 1, 2, 2. And then after you get this back, what do you return for the overall? How do you solve this problem now?
You push 3 on twice.
Yeah, exactly. So then you just push 3 twice. Times 2. Okay. This is really similar to the example that Marty gave in class, right? M&Ms.
So you'll just go through until. So the base case would be if it's empty, return nothing.
Right,
and
yeah.
then the recursive is you call it, and then you push the last thing twice, and you do that until.
Exactly. So if stack empty, then just don't do anything. Then just return. Otherwise, you pop off the top, pop off top, and then call stutter stack on remaining, and then push twice.
Mine.
Okay. All right, let's quickly code this right now. So let's see, void stutter stack. Super important. Make sure it says it accepts a stack of integers as a parameter by reference. Does it say by reference?
I think so. It said so here.
Okay.
These are kind of different than.
Okay, never mind. Yeah, I'll tell Marty about this.
Yeah.
But yes, make sure if the question says by reference, make sure you put the ampersand there. Okay. Yeah. Okay, 3 point, right? So and the exam only had a 50 points, so it's like literally 2%. But okay, so stutter stack. How do we code this up?
Well, if stack.empty,
Okay, it is empty. Then
return.
don't do anything. I usually prefer just write out the base case explicitly, even if it means if this is the base case, don't do anything. Explicitly write return. Okay, because that makes it really clear. When do you stop? Okay. If you look, the solutions, they'll say the opposite, which is like, if the stack is not empty, do this. And then implicit is if it is empty, then just don't do anything. Okay. But I strongly prefer explicitly write out what happens. When do you stop? You explicitly say stack is empty. All right. Otherwise, you pop off the top. How do you pop off the top?
Stack dot pop.
Okay. And then
We want to track that as an integer, right?
yes, that's a very good point. Yeah, we have to track this into val or
And last num, perhaps,
sure. Let's call it as num.
equals stack.pop.
And then
And then we recursively call stutter stack, stutter stack,
What's that?
stutter stack stack,
And then
then just
go stack
stack push last num.
push last.
And we do that twice.
Great.
We just write that out twice, like stack push last on next line, stack push last line.
Yeah. If you have to push it in like 10 times, then obviously you use a for loop.
Right.
But if it's twice, then you literally just push it twice. Okay? Does that make sense? Quick question. Do we return anything here?
No.
Yeah. Okay. So in your recursive functions, think about what you have to do with each one, right? Sometimes you have to return something. Sometimes because you pass the collection by reference, so you don't actually have to return anything. You just change the parameter exactly as is. Okay.
So if the stack is empty at the start here, it will try and return, right?
Yes.
But you can't return from the void.
Yeah, that's what I was.
Oh yeah, that's a good point. So yeah, so we're not actually returning anything because we're just saying return semicolon.
So that doesn't. It
Yeah.
just breaks it.
Yeah, it just breaks. Yeah. It's a nice way in your void function. If you just return semicolon, it just stops the function immediately.
Can you not just write break, or is that?
Break only works in a loop.
In a loop.
Yeah. Okay. Oh yeah, I see that a lot on exams as well. Okay. So oftentimes in recursion, if you just don't want to do anything, if base case return. Okay, and then we can run this. Yeah. Okay. Yeah, and then you also mentioned a good point, which is what happens if you just initially pass in the empty stack? Well, the base case just immediately returns, so it gives you the empty stack. Okay. Ooh.
That sound.
All right, let me know if you have any issues. Was the issue the ampersand? Maybe.
Perhaps I didn't.
Okay, we have 5 minutes left, so let's just quickly do a recursion trace. Okay, I'm gonna do step 1 in like. Okay, actually, hi SCPD students. Look at the mystery B recursion trace problem number 2. Okay, we're just gonna quickly talk through this because we don't have much time. But let's see. Okay, recursion mystery. So so think about this. What happens if you pass 4, 1 as the parameters? So here, if you passed in 4 as x, y as 1, what happens?
Returns 4.
Does it return 4?
No, just prints it out.
It prints, right? It prints 4. Right, because y is 1, so we just immediately go to the base case. Does that make sense? Okay? So yeah, on the recursion, there's going to be a recursion trace problem. There's usually 2 or 3 parts. One of them is going to be a free beat. Okay, literally, what happens in the base case. Okay, the other ones are a little bit harder to track. Okay, so let's do 8.2. I just want to quickly write how you might approach a problem like this. This is a case where you actually want to think about what happens in each stack frame. Okay, on an exam, you don't want to actually copy the entire code over here. So what I like to do is I like to say, okay, there's a base case. This is a quick summary. Base case. First print. Recursive call. Second print. Okay. This is like a bit like an outline of the function. Okay. And then we have a separate console over here. Okay. So let's see. If you passed in 8.2, what happens?
It prints 16.
Okay, so let's see.
16 command.
Yeah, you skip the base case. You go to the first print where it prints 8 times 2, which is 16, comma. Right? And then it makes a recursive call on what?
On 8.1.
8.1, okay. Okay, so how I like to draw this is, okay, now you have a new stack frame where this recursive call calls mystery B82. Okay? Base, first, recurse, second.
Well,
Okay.
8.1 in that case.
Yeah, 8.1 in this case. Now, one thing to remember, and this is what almost everyone messes up. When you make the recursive call over here, what happens when this function is done?
Goes back.
You go back where?
To the next line.
Yeah, you have to go back here. Okay? Yeah, what some students think is, oh, I reached the base case, I'm done. That's not the case. When you reach the base case, you have to go back through all the function calls again and make sure you have to go back to the function call and do whatever's after that. Okay? So for what happens over here?
It goes into the base case now.
Base case? Yeah, it goes into 8.1, right? Okay, so 8.1, and what does it print?
8.
8. Comma, right?
8
No comma?
Yes.
No comma.
No comma. Yeah.
Okay, prints 8. And then it just skips over all these. What happens after it skips?
It goes back into the
Right after the recursive call into the second print.
Yeah.
What happens in the second print? What do we print?
8 times 2.
Yeah, don't forget, our x and y are now these two, right? Not this one's gone. This one's dead forever. 8, 2, you print 16 again. Okay?
Without the comma.
No, because it's the
The comma's before. Okay. Perfect.
Yeah. Well, most students miss this one because they think, oh, I'm done with the base case. I don't have to go back. Okay? Yeah. So I like drawing this because it makes it really clear, oh, like how many, like you remind yourself to go back to here when you're done. Okay? Yeah. I'll just tell you immediately, the recursion trace problem is going to test this thing. So this is the thing you do not want to miss. Okay? There's going to be stuff after the recursive call. You cannot miss that one. All right? In our last minute, do you want to try the third one? Just, that one looks really painful. I'll just tell you a quick story. When I took the class, Marty gave us a recursive function where you had to trace 26 steps.
Okay.
Yeah. He gave us a DNA sequence, and then we had to like parse the DNA sequence. Yeah, and then it was just really annoying.
And you did this 26 times?
Yes, and I spent 10 minutes doing it once, and I did it twice. I got 2 different answers.
Oh.
It was not worth it. No, but he probably won't give that kind of question. Yeah. So okay, yeah, try that, and then tell me what you get.
This
The
one.
third one. So on the
3,
3, 4, yeah.
I already did it.
Oh, you did it.
Yeah, that's
You're done.
now that makes sense. Drawing that out. Now it's like boom, 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 boom. Yeah. Just a little
Okay. Yeah. What answer did you get?
12, 9, 6, 3, 6, 9, 12.
Yep. Awesome. Yeah, you're exactly right. Okay. So important. When you do a trace problem, definitely draw this. But when you do a code question, this will confuse the heck out of you. Right? Imagine, okay, I do a stutter stack, I do one step, then I do another step. Wait, where's my code exactly? Like, what do I write? Yeah, you only focus on this one single stack. This is your code. All right? Cool. Here are the solutions. Here we go. So we didn't get to cover the challenge problem, which is great because that problem confuses me too. But number 7 is a pretty challenging problem. Okay. I'll tell you, I don't know how to do it iteratively. If you told me you can't use recursion, I have no idea how to do number 7. You probably could, but it's pretty complicated. Okay, but if you use recursion, you can solve it in like 5 lines. Okay, it's a challenge problem. You'll if you do like an interview at a tech company, like you might see this problem. Okay, because it is a pretty famous problem. Next week we'll cover a variant of this problem called longest common subsequence. It's a really cool problem. It has a special place in my heart because when I interviewed for this job, that was the problem I did. So we'll do that problem next week. Okay. Cool. Before you leave, I just want to say one more thing, which is this is an advertisement for a class. So CS106L, Marty will mention this like 8 weeks from now, but I just want to say this right now. CS106L is a class which teaches you standard C++ programming. So we won't use the Stanford libraries. We'll essentially use the real STL libraries that like professional programmers they use. Okay. Oftentimes when I came out of 106B, I was like, okay, great. I can use the Stanford libraries, but I have no idea how to like actually use the standard vector map and so on. The class is offered in the fall, and I'll be co-lecturing with someone else. All right, so it's 1 unit, yes, and it's pass-fail, and there's 3 assignments. You have to do 2 of them. Each assignment is like a third of one of the current assignments. It's like pretty chill. Yeah, you can put as much or as little work as you want, but you'll learn a lot. I really like the class, and please take the class. Okay. Cool. All right. I don't know about SCPD students. I don't know if you're allowed to take that class, but if you're interested, check out the 106L website. Okay. Where am I looking at? Some camera. Okay. Yeah. Thanks for coming. All right. Cool. And then let's see. I don't think he's turned in his assignment, so